Okay, so we have started dealing with this injection mold design, and in that we discussed yesterday about different types of injection molds, right? So in that we discussed single cavity, multi cavity, two plate, three plate molds. Okay, and we have seen the pros and cons of each particular category. Okay, now then we discussed about the feeding system also. Feeding system in the sense how the material is fed to the mold cavity getting. Okay, then we discussed about the temperature control system. Basically in this we discussed about the, we focused on the cooling system more, because it is actually representing the microstructural growth of the particular component. Then we discussed about the ejection system also. So ejection system is also very important, because once the product will be produced or the manufactured, it is very important to easily or properly remove from the mold cavity. Because what happens while removing the product from the mold cavity, so there may be possibility that this there will be a friction in between these two surfaces, surface of the mold cavity and the surface of the product, so which will destroy the shining of the surface, or maybe any part of the component also. So along with other system or other mechanisms, the ejection mechanism is also very important one. Then okay, so here we discussed everything, that how feeding mechanism work, how ejection mechanism work, and how the cooling system also works. Okay, this is the general design of the injection mold. We discussed about the ejection system, also types of ejection system. Possibly there will be a MCQ type question based on this ejection system, types of ejection systems. Right, then feeding mechanism we discussed. What is the role of feeding mechanism? And right. So yesterday, a single cavity, multi cavity. Okay. While discussing single cavity, multi cavity, I told you some of the common points. Based on that, you can explain everything. No need to even read in a detail. So here I told you that what happens. Basically, there are two basic types are there: single cavity and multi cavity. Single cavity and multi cavity. Okay, this is single cavity and multi cavity. Basic parameter to divide these two category is that demand, or you can consider this as a productivity. Okay, so if demand of the product is more, if the productivity requirement is more, that means if you want more number of products in less time, productivity in the sense more number of product in less time. Okay, so productivity is defined with respect to time parameter. So when you need the higher productivity, that time you need to manufacture the more number of products at a time. Okay, so that should be the thing. So for example, if this is a larger mold, so you should be able to manufacture like this, four number of products at a time, or five or six, depending on the size of the product. Getting it, and this can be easily managed by providing central runner and sprue type arrangement and effective gating system. You can provide the proper raw material to all the cavities, and you can have the maximum number of products at a time. Okay, so this will come under the category of multi-cavity. And when the product size is larger, okay, the basic difference I told you. When there are very small size product, obviously a small size product will have the less cost. Getting small size product will have the less cost. So you cannot invest more time, more what you cannot invest more time or more money or even more material for the manufacturing of that component. So in case of short, like for example, this is the single bottle. Okay, this is now single cavity type. This entire product is a one part, but if you want to manufacture only cap of this bottle, because obviously cap will be manufactured separately. Now this cap is a very small part, hardly costing 1 rupees or less than 1 rupees. Okay, so For such kind of products you cannot go for the single cavity type design, because the final cost of the product is very less, right? And as such, no any performance, whatever the performance parameters are required, so that intensity of the performance parameters is not high. I mean, we don't require so high strength, so good surface quality. Okay, so that is not desired in case of the cap of this bottle. Even moderate parameters are sufficient for this kind of product. So where the cost is very low, size of the product is very less, and performance parameter requirement is not intense, then that time you can go for the multi cavity. Okay, but the major hurdle for the multi cavity product is the size of product and cost of product. Okay, with these two parameters you can divide the these two categories, single cavity and the multiple cavity. Then we have seen another one parameter also with which this is classified, that was two plate and three plate. Two plate and three plate. Okay, even we have the figure for the same here. Okay, here it is clearly given two plate and three plate type injection mold. Okay, now if you can check here, see, this is the three plate mechanism mold, and this is a two plate mold. What is happening here? This additional one plate, a runner or stripper type plate. Okay, additional one plate, and here are only two plate molds are there. Half part which is a moving one is the top one, and this is a fixed one. Okay, lower part. Here also this is a fixed one, this is moving one, and this is moving one. Okay, only now what is happening in case of three mold, we are having two parting lines. Here is one parting line, here is another parting line, and in case of two plate mold we are having only one parting line. Getting it right? Now what happens? Now in case of three plate mold, in case of three plate mold, this sprue or runner mechanism is given separately. So what will happen? These impressions of this mechanism will not be there on this product surface. Here is the product, here is this kind of, here is the product. Are you getting? Okay, so on this surface you will not get the impression of this gating system, but in case of two plate mold there will be impression on this gating system. Okay, this one. Okay, we'll see, at the end you can remove it while going for the finishing operation, but obviously there are going to be some marks on the surface. If you want to still go for the two plate mold, one thing you can do, that this surface on which this gating system marks are there, this should not be a facing surface. This should not be a facing surface in the sense a main surface, because for any product you are having one facing surface. Suppose this one is a facing surface which is viewed by the user, and this is a backside surface. Okay, which will be always at the back. So you can put the runner or the gating system or the this gating mechanism at the back side. You can manage the product that way if you are going to use the two plate mold. But at all, if you don't want any mark or the any impression of the gating system or the gating mechanism, you will have to go for the three plate mold. Looking to the complexity, obviously more number of moving part, that means more complexity. So this complexity will be more in case of three plate mold, it will be less in the two plate mold. Okay, so then pros and cons accordingly. More complexity, so skilled labor is required here, so here less skilled labor can also work out. Getting it? Okay, three plate mold costing is going to be a more, because more number of setups are there. In case of two plate mold, costing is going to be less. Initial investment will be also more in case of three plate mold, and it is less in the two plate mold. Similar kind of pointers will be there based on this mechanism. Right, so that's how this two plate and three plate molds are defined or differentiated. Getting it? So basically, if you want to have the segregation, two three categories are there. First one, this cold runner mold, hot runner mold, that also we discussed. Second is three plate mold, two plate mold, and third is single cavity and multi cavity mold. Okay, so there are these three categories. If you will get the question in the exam, then you will have to mention all the three categories, right? So now, today the next point, if you see, the next one is the last point, that is the numerical, okay, or the design procedure for this injection mold of the simple component. Getting it? Okay, so today possibly we'll go for the formulation required for the design of the injection mold for simple component, and if we'll get the time, we'll start the numerical, or else we'll see it in a next lecture. But just see the formulation properly, because while solving the problem during the practical hours, you need this formulation. So understand the formulation properly, and see similar kind of problems we discussed for compression part also, and while designing the simple components also. So if you see the difficulty level of that problems, so it is very nominal. So very I mean, it is nothing like that as a like design part, because actual design problems you might have solved in the your machine design. Getting it? Okay, so that kind of assumptions and that kind of lengthy problems are not there. Simple formulas are there. You just, you will have to put the values, two three assumptions will be there, and you will get the entire solution, right? So let's see now, to we'll have some this formulations required for the injection mold design. Okay, so we'll see now injection mold design. Okay, for simple component we are looking after only simple component, right? So now currently the component that we will consider is this kind of component. You can consider this as a cap. Very simple components we are considering, right? So this is a simple components that we will consider. Just a minute. So size is same. Size is same. Okay. So this height is around 2.05. This smaller height, sorry, this is 2.15, and this is 2.05, right? Centimeter, all the dimensions are in a centimeter. This internal dia is around 3.3, and this one will be obviously, because in the this dimension, vertical dimension only, you will get the thickness of the component. Getting it? Okay, so that's how the simple component, right? So that's how the simple component is there, and for such kind of component you will have to design the mold. Okay, so basic procedure is there, whatever may be the component. Just for your understanding, I have shown you one component. First of all, what the things you will have, uh, not a first point, given data. Okay, so in any kind of problem you will have injection pressure, okay, which will be given in the problem. Okay, so injection pressure will be given, then density of the material used for the component will be there, density of the material. Okay, injection pressure P, density of the material will be given, right? Now see, the first part that you need to calculate is, as regular, weight of component. Weight of component, because based on that weight only we are going to design the mold, right? weight of component. Now see, now if you check the weight of component, now this is, here is the cavity. Okay, a larger diameter is 3.4, smaller diameter is 3.3, so wall thickness is around 10. Getting it? Okay, so we want the weight of the component. Now based on this, see what we are having. We are having density of the material, or you can consider this as a density of component. Okay, material will confuse you. Right, density of material or component. Right, so see, this density is given in the kg per meter cube. If you multiply it with the volume, you will get the weight, because kg per meter cube and volume will be a meter cube. So meter cube will be cancelled and you will get the weight in the form of kg. Getting it? Okay, so simply you need a volume of the product and you have the density of the product. So how I will calculate the weight of the component? So simple, weight of the component is equal to, so with respect to this product will define the things. Getting it? Okay, obviously most of the products will have the cavity, so that we need to consider separately. So how I will write, outer volume minus inner volume, because at the inner there is a cavity. Outer volume minus inner volume, and this entire multiplied by density. Getting it? Okay, so the first part you will have to calculate is the weight of the component. Just calculate the outer volume and the inner volume, make the subtraction and multiply with the density. Okay, outer volume here will be with respect to 3.4 diameter and inner volume will be with respect to 3.3 diameter. Are you getting? Okay, with the example we are understanding. We will solve the problem also, no problem. Getting? Okay, so through that you will get the weight of the component. Then second thing you need to calculate as regular is the projected area. Okay, simple, right? So projected area is the facing surfaces of the 3.4 diameter. Facing surfaces with the 3.4 diameter. So see, with respect to this, see, if a rectangular section will be there, so formula will be obviously changed. Getting it? Formula for the calculation of area will be changed. I am calculating with respect to this example or this component. Okay, so being a circular one, here will be 5/4. If we are considering larger one, d1 square, or simply d square also you can write. Okay, so projected area, see, this formulation will not be fixed. Are you getting? I am defining it with respect to some component. This area we have defined for the circular cross section. If you are having a square cross section, you will have the side square. Okay, so projected area will be different. Getting? Now now see, in case of injection molding, we'll discuss it in a separate slide. See, in case of compression molding, I will compare and then I will tell to you. In case of compression molding, if you are checked, mostly we are going for single component manufacturing. Getting it? Okay, so what is the problem? If suppose a large size mold is there, 4 components we are going to manufacture. Through compression molding, we cannot ensure that there will be equal pressure on all these 4 cavities. That is the issue. Equal pressure on this 4 cavity, we cannot ensure that. If there is a, this is the mold, single product, single cavity is there, so pressure will be concentrated. Compression pressure will be concentrated on a single location, so it will be evenly distributed throughout this component. But this is not, this cannot be ensured properly with respect to this multi cavity. I am discussing about the compression mold. But see, in case of injection molding, this can be ensured properly because of the setup of the injection molding. See, injection molding process itself is designed for manufacturing or more number of products in a shortest time. Injection molding, the basic purpose is not for manufacturing a single component at a time. If it is a large, another case. But injection is defined for multi manufacturing or multi cavity manufacturing. Okay, so aim is only that you should be able to manufacture number of products at a time. Getting it? Okay, so that's what the aim in the injection molding, and that's how it is designed. Getting? So in case of injection, always mostly you will have more number of cavities rather than a single cavity. You will have more number of cavity in case of injection molding. So now in compression molding we calculated a projected area for single cavity. Here we are having a more number of cavities, so obviously we'll have to go for that many times the projected area. Are you getting my intention? In case of injection molding, preferably or most of the times we are having multi cavity setup. As we are having multi cavity setup, we have to go for that many times the projected area. Okay, so I told you about the projected area for single cavity, but we have to now go for the projected area for multi cavity. Okay, so that will be called as a total projected area. Total projected area. Now, one more thing. Now, while calculating this project area, see, this is the simple components we are considering. Suppose, for example, we are going to manufacture 4 number of products at a time, okay, through the injection molding part. Now, in this mold design, this what is this? This line I am showing always. This is nothing but the gating system. So in case of compression molding, we have not seen this gating system, but here it is required. Here it is required. So this is a integrate part of this mold design. So obviously we have to consider the area required for this gating system also. So along with this, you have to consider the area for the gating system also, because this is going to be a part of this mechanism. Okay. So while calculating the total projected area, apart from the area required for this cavity, this cavity, this cavity, this cavity, you need to calculate the area for this mechanism also, gating mechanism also. Now, not required to calculate exactly, but at least we can have some spare area for that. Okay. So general consideration is that projected area for gating system. Projected area for gating system will be 10% of projected area. Means whatever projected area you have used for the component, so 10% of that projected area will be for gating system. Okay, so this 10% you will have to add while calculating the total projected area, right? So this also will consider. Are you getting the things? Gating system is a part of mold design, so that we have to consider this total projected area. Okay, so now I will write here total projected area. Total projected area equal to projected area for single cavity. Are you getting this? This will give the projected area for single cavity. So projected area for single cavity plus projected area for gating system. Projected area for wait a minute. Projected area for gating system. Okay, and this will be your projected area for single cavity. Are you getting? Area of single cavity plus area of gating system connected to that cavity. So this complete box will give you the net area for single cavity multiplied by, we have multi cavities, multiplied by, here I am writing these things, multiplied by number of cavities, number of cavities. What is the thing? Okay, so net area for single cavity will be area of that cavity plus area of the gating system. So that's how you will get the area for the single cavity, and then you will have to multiply it with the number of cavities. Okay, now, so that's how you will get the total projected area. Next one, machine load capacity, machine load capacity. Okay, now injection pressure is already given. Okay, here I told you injection pressure. Okay, P is already given, which is required here. So machine load capacity you will have to calculate. So machine load capacity, see, we know the injection pressure, with which pressure material is forced, and this injection pressure where it will act. See, injection pressure, it will act on the projected area. This is this concept is similar as like the things we discussed in the compression molding. Pressure in the compression also, pressure was acting on the projected area. Here also injection pressure will act on the projected area, but only thing is that here we have to consider total projected area. Okay, so machine load capacity equal to total projected area multiplied by injection pressure. Injection pressure will be given in the problem, and total projected area you can calculate easily. Okay, so that's how you will get the machine load capacity, right? Easily you can calculate the machine load capacity. Now this machine load capacity you will get in terms of kg, or you can convert this in the or ton. Mostly machine load capacity is represented by ton. Okay, so whenever you will get the kg, you will have to convert it into ton, right? So you will get the machine load capacity in a term. Now in the given data, one more thing will be maybe given, or maybe sometimes we'll have to assume. Mostly what happens, machine is not available with odd capacity. Machines are available with the capacity of like uh, 20 ton, 30 ton, 40 ton. It will not be available like with 14 ton, 19 ton. Okay, you know the things, because if you check the machines available in the market, any kind of machines, so these are available with the rounded figures, right? So additionally you will be given the available machine. So suppose your answer will be, for example, this kg I will remove now. Your answer will be like 16 ton. Your machine load capacity will get 16 ton, but that 16 ton machine will not be available. So in the figure, sorry, in the problem, it will be mentioned that machine is available of 30 ton. Machine is available of 30 ton. Getting it? Okay. So that figure now you will have to consider. That figure now you will have to consider for the reverse engineering purpose. Okay. Now quite different problems. Just understand properly. Suppose machine is not available for 16 ton. It is available for 30 ton. Now what will happen? Because high capacity machine is available, these parameters are going to be changed. What is our formula? Machine load equal to total projected area into injection pressure. Getting it? Okay. Now you are having some defined machine load, that is 30 ton. Okay. So you will have to redefine now projected area. Are you getting? You have calculated the project. You calculated the projected area. Based on that, you calculated the machine ton capacity also. But available machine is with the different ton. Okay. See, if you will get here 29 point something or 30, no problem. It is matching with the available machine capacity, so you can go ahead. But when it is not matching, now what is going to happen? This total projected area, injection pressure will be same. Let the machine will be of 30 ton, 20 ton, 30 ton or 40 ton, whatever it may be. But the injection pressure we are using for that component will be same because it is based on the component, not based on the machine. Okay. So injection pressure will be same. So we know the injection pressure, we know the capacity, then you will have to calculate revised projection area. You will have to calculate the revised projection area. Okay. So this calculation is with like this: available machine load, and then you will get finally available projected area. Getting it? Okay. You have calculated this projected area, available projected area with available machine load. So you will get the available projected area. Getting it? Okay. Now next parameter is to calculate wall thickness, and how you will get, see here now, mold wall thickness. Okay, not the product thickness, mold wall thickness. What is the mold wall thickness? Suppose this is the mold, here is the raw cylindrical product. So this thickness, this is called as a mold wall thickness. Okay, this wall thickness, are you getting this distance from this edge to the edge of the component? Okay, so this wall thickness you have to calculate. Now just understand here how you will get this wall thickness. You know the area, this area, and once you will get this complete area, are you getting my intention? You know the area of the cavity, you know the area of this large mold, subtract that and you will get this one. Are you getting area or the dimensions? Area or the dimensions. So now what is happening? You will have available projected available projected area. Getting it? Okay, suppose you will get available projected area as 100 centimeter square. Available projected area is 100 centimeter square, and consider that your mold is of square type. Now some assumptions you will have to make. Okay, obviously it will not be triangular, or it might be rectangular or square. Okay, better to go for the square size. Okay, so you are having the square size mold. Okay, so you know the area, total projected area of the mold, not of the component. Okay, you know the area. Can you calculate the side dimension of the this, what you can call, from the area you can calculate the dimension of the side or the wall dimensions. Okay, simply 100 centimeter square area for the what, square. So its side dimension will be 10 centimeter. Reverse engineering. Okay, because formula is side square. Getting it? Okay, so by considering square cross section, I calculated the side. I calculated the side. Getting it? Okay, now I know this side is 10 centimeter, this dimension is 10 centimeter, this dimension is 10 centimeter, this dimension is 10 centimeter, and this dimension is 10 centimeter. Okay, and I know the cavity size also for the product because already we calculated it. I know the cavity size also product. Okay, here also you can see this 3.4. Are you getting this 3.4? This is the cavity size, larger size, right? So I know this size. So this diameter I know. This diameter I know. Okay, other else we'll draw some larger figure. Okay, so 10 centimeter this, 10 centimeter this, 10 centimeter this, 10 centimeter this, and here is the product located. Okay, equidistance from all surface, equidistance from all surface, keep it in mind. So I know this diameter, and what I want, wall thickness. Where is the wall thickness? Here is the wall thickness, this red colored. This is the wall thickness, this is the wall thickness, this is the wall thickness. Can you easily calculate that? Simple. This entire dimension is 10. Subtract the diameter. Suppose diameter, what I'll write, 6. 6 centimeter is the diameter. So total dimension is 10 centimeter minus 6 centimeter. You will get 4 centimeter. So this 4 centimeter, but how the 4 centimeter? It will be distributed at the both the side. So this will be 2. This will be 2. So 2 plus 2, 2 plus 6, 8 plus 2, 10. So this will be 2, this will be 2. Got the things? So that's how you will get the mold wall thickness, which was the last parameter, mold wall thickness. Getting it? Okay. If nothing is given, consider square cross section area. Okay. Right. Are you getting? If suppose for the same thing, I will explain differently. Suppose this is the area you considered 10, 10, 10, 10. Okay. And you have multi cavities. What I'm saying, you are having multi cavities. Suppose you are having 2 cavities. One is here, another is here. Are you getting? Okay. So that time, you know this diameter, this diameter, this diameter. Obviously, products must be same. This diameter, suppose here it is a 2. It is a 2. Okay. So how you will place it? You will place it equidistance. Obviously, this distance will be same. This one and this one is going to be a same, and this one. Okay. Right. Only you will have to maintain. Only you will have to maintain a proper distance here. Okay. So try to go for at least the same distance. So this 2 plus 2, 4, remaining is 6. It will be a 2, 2, 2. Getting it? Got the things? You go on more number of cavity, you can split the dimension. You can split the dimension. Somewhere you will have to make the assumption. Okay. Someone will consider this as a 3. Okay. Accordingly, these dimensions will vary. Only keep it in mind, this cavity should not be so close to this corner. This cavity should not be so close to this corner. Neither this, or even this cavities, both the cavities should not be close to each other. Otherwise, crack will generate from that point. Getting it? Okay. They should not be very close to this corner, this corner, this corner, this corner, or even close to each other. It should not be very close to each other. Okay. By considering that, you can easily calculate the dimension. So that's what the procedure for the solving this injection mold design problem. Got the thing? Okay. So these are the things. Only very less number of parameters are there. Wall thickness is there. With available machine load, you will have to calculate total projected area. If the available machine load and the calculated load. See, here we have calculated where it is. Here we calculate. If it is also 30 ton, this is also 30 ton, then same area you can consider. Okay, no issue. If it is different, then available. See, in the machine design, or I think in the machine design only, you are having calculated stress. Calculated stress, and one more parameter you are having, permissible stress. Are you getting? Permissible stress? So with this permissible stress only, you are calculating factor of safety. Getting it? Okay, so similar kind of, but only approach is different. Same uh, procedure, but only approach is different, right? So this you will have to calculate total projected area, individual projected area, consider the gating system area while calculating the projected area, and this you will be given in the problem. What will be given? Injection pressure, density of component, right, and the design of the component. So from that you can calculate volume, and from the volume and the density parameter you can calculate the weight of the component. Okay, so that's what for the today. In the next lecture we will solve one problem by using this process, and then we'll conclude the this unit. Okay.